In this video, we'll create a custom SDF operator using code from ShaderToy. We'll be using RayTK version 0.27, though other versions should also work. Check the video description for a download link. This tutorial will require at least a basic familiarity with GLSL, though we will mostly just be copying and pasting code. Start by dropping the toolkit talks into your project. First, we'll set up the renderer. Open the palette using the Alt-R shortcut and create a RayMarch Render 3D. And then create a null top so you can see the output. I'm going to set the resolution here to 1000 by 1000 just so that it fits in this side panel. With the renderer selected, use the Alt-Shift-R shortcut to open the RayTK Editor Tools menu, and then choose Add Look at Camera. We'll update the camera settings later on, so we can just use the defaults for now. In most of the other tutorials, we've based our scenes around SDFs that are already available in the toolkit. But what if you find one on ShaderToy and want to include that in your scene? Of course, you should feel free to reach out to request for it to be added to the toolkit, but if you want to experiment with it on your own before that, you can do it using a custom operator. Custom operators allow you to provide your own snippet of code and use it within a RayTK scene. Open the palette again and create a custom operator. When you create the custom op, it will automatically create two other operators. Above the custom op is the parameters comp. This is where you will add custom parameters that you can use to control the operator. In regular ROPs, those parameters are included on the ROP itself, but for custom ops, they're kept separate. For reasons that will become apparent later, I'm going to move the parameters comp to the side here. Below the custom op is the function code dat, and this is where you'll add the code to implement the custom behavior. On the custom op itself, there are some parameters that control things like the type of coordinates that it uses and the type of result that it produces. By default, it's already set to use 3D coordinates and return an SDF result, which is what we want, so we can just leave those as they are. There is also a page of parameters called tools, which can perform various types of actions to modify or update aspects of the operator. The code that we'll be using will come from ShaderToy. Specifically, we'll be using the Rhombus 3D SDF from Inigo Quiles or IQ. IQ's code is the basis for much of RayTK, so if you look through his shaders, you may recognize some things. At some point in the future, this SDF might be included in the toolkit itself, but for purposes of this tutorial, we're going to create it ourselves. Check the video description for the link to the shader. When you're looking for SDFs on ShaderToy or elsewhere, what you're looking for is a function that returns a single float value and has a vec3 or possibly vec2 if you're dealing in 2D parameter representing the position, typically called p, and it may have some other parameters. So IQ typically names these functions starting with SD, and many other people follow that convention as well. So in this case, we're going to be using this SD rhombus function. Not all shaders that are doing this kind of 3D shape are going to be using RayMarching though. So if you can't find a function like this that returns a single float value, it might be using a different approach like ray tracing, which isn't compatible with RayTK. Now that we've found the code that we want to use, we'll integrate it into our custom operator. So copy the SD rhombus function and this comment above it, and then go back to Touch Designer. Before we start working on the code, it will be nice to have some GLSL syntax highlighting. Depending on the version of RayTK that you're using, This might be automatically set up, but if it isn't, on the code dat, under the common page, change the content language to GLSL. And we're also going to connect that customOp to the renderer in case you haven't already done that. So I'm going to be using the textport panel to edit the code, but you could also use an external editor or just zoom into the dot and edit it in place. In the code, above the thisMap function and below that top comment, we're going to paste in our code from ShaderToy. The thisMap function is the main function for the operator. It's what the renderer calls to ask about points in space as it's marching rays through the scene. The p parameter is the coordinate in space. Depending on the type of ROP, this could be a vec3 or a vec2 or possibly even a float in certain cases. But since we set it to use 3D coordinates, we can assume it to be a vec3. But you should still keep the type coord t, this placeholder here. So we'll see later what that means for the shader. The CTX parameter is for more advanced features that we won't be using in this tutorial, but you do still need to have it in the function there. So clear out the code in the body of the thisMap function, and if you click outside of that or save it if you're using an external editor, you're now going to see the error checkerboard in the output. And that's to be expected since we haven't filled in the code yet. Enter the following code in the thisMap function. Float d equals SD rhombus, and that's the name of our SDF. And pass in p, and then we're just going to pass in the same parameters that it's using in the function, so LA, LB, H, and then if we scroll over to the side here, RA for the last one. Then semicolon, and going to return and call create SDF, and passing in that D. So what we're doing here is calling this SD rhombus function. We're passing in the position and several other parameters that we haven't set up yet. And that is creating a distance value, which we're putting into this variable D. Then we're calling create SDF, passing in that distance to wrap the distance in an SDF data object, which contains other properties like material settings, though we're just using the defaults for all of that in this tutorial. Next, we'll need to come up with values for those other parameters. In this example, IQ included a comment that kind of describes what those mean, but that won't always be present. Many people that write shaders, especially IQ, like to use really short names for the variables and parameters, which can make it difficult to understand what they represent. So you may need to experiment with different values to understand what they do. To get some initial values, we can look at the original shader. Going back to ShaderToy, and we can find where this function is being called, so down here, and it's just using these 4 literal numbers. So we can copy those and then go back to Touch Designer, and inside our thisMap, above our call to the function, we can add a comment and just paste those in. Next, we'll create named variables and fill them in with these values. So first, we're going to create LA, set that to 0.6, then LB, set that to 0.2, then H, and set that to 0.02, and finally RA, also at 0.02. And note that different functions that you find may have different types of parameters, so these might not all be float values, might be vectors or something else. Now, if you click out of that, you're going to see some sort of result in the output, but we're just seeing the side of it, so let's move our camera. Over on the look at camera, we're going to increase the Y position to 2 and then decrease the Z to 3. So now we've got a view of our shape there. Now that we've gotten the rhombus to look like it does in the original shader, we can expose the parameters so they can be adjusted without having to change the code. We'll start with LA. If you change the value of that in the code here, for example, to 0.5, you can see how it's controlling the width of the shape. At the top of the code dat, there's going to be this comment here starting with this @ symbol, and this is an example of how to define a parameter for the operator. So we're going to replace this name with width, capitalizing the W, all the rest lowercase, and then we're going to set the default here to 0.5. And note that this chunk here has to be valid JSON, so you need to have this 0 in front of the 0.5. Any of the properties of the par class can be set in here, including clamp min, clamp max, and so on. And you can look at the documentation for the par class on the derivative wiki for details. On the customOp, on the tools page, we're going to click create missing params. Now if we look at our parameters comp, we'll see a new width parameter. We can right click that and just choose reset to set it to that default value. Now that we have a custom parameter and the customOp is aware of it, we can reference it in the code. On the line that sets LA here, we're going to replace this number with capitalized this, so all uppercase, and then underscore, and then width, capitalizing the first letter and the rest lowercase. Make sure the capitalization matches this exactly and the name of the parameter is the same as what you used up there. Then on the parameters comp, try changing the width and you'll see the rhombus update in the renderer. Now we'll repeat this for LB, which we can presume represents the other axis, which we'll call the height. So we're going to copy this line, paste it, and then change the name to height. Then on customOp, we're going to switch on this auto create missing parameters so that we don't have to click this button every time we add a new one or change something there. Then in the code, we're going to replace this here with this height. Now we can change that on the parameters comp here. Then for H, try changing the value there, say to 0.05, and you'll see that it's controlling the thickness there. Now IQ called this height there, but we're already using that name, so we're just going to call it thickness instead. So we're going to copy this line up here, paste in another copy of it, change the name to thickness, and then for this one, we're going to change the default to 0.05 and the norm max to 0.5, since we're typically going to be using smaller values for that. Then down in the code here, we're going to put in this underscore and then thickness. Then we can change value there, and that will influence the thickness of our shape. Then for RA, if we adjust that there, again, try something like 0.05. It's not quite clear there, so we can increase it even higher. So that looks like it is rounding out the shape. So we can call that rounding. So again, we're going to copy this line here and rename it to rounding. and we can keep the other settings as they are. And then in the code, this underscore rounding. And then we can adjust that to control the expansion and rounding of the shape. So just set that back to the default. And there we go. So we have a rhombus SDF with parameters to control all the different properties. We can use this anywhere in a RayTK scene where SDFs can be used. When you're working with custom operators, it's likely that you'll encounter errors in the code. To reproduce this, we'll add some errors to our code. So we're going to change one of the variable types, like LA here, to say vec4, and then down where we're calling this rhombus function, we can just delete the last s so that it doesn't match the name. So now you'll see the error checkerboard in the render output indicating that there's a problem in the shader. On the renderer, we're going to scroll down and click the Inspect button. This will open the Inspector tool. At the top of the inspector, you'll see this red message indicating that there's an error in the shader. If it isn't already on the shader tab, switch that tab by clicking the tab here, or you can click the error message at the top. The bottom area of this tab shows the results of the shader compile. And in this case, that's going to include the error message. So we can see that on line 114, or possibly a different line depending on which version you're using, there is an error saying cannot convert from temp IP float to temp IP vec4. So key part there is you can't convert from a float to a vec4. Now, in our original code, it was way less than 114 lines. So this means that the line number is in the final shader that is generated by the renderer, which includes a modified version of what we typed in, along with lots of other code. So scroll down to that line in the top code panel. There we can see a function named customOp1, which matches the name of our custom operator. Some parts of it have been replaced, like the return type, the coordinate type, and so on, as well as the name of that function itself. But generally speaking, it should look pretty similar to our original source code. On the line indicated from the error message, we can see that we've got this vec4 variable, and we're assigning a value to it from this parameter name here. So the value that it's using here is a float, but it's trying to put it into a vector4, so we need to change the type of that to float. And we can't edit it directly in the inspector, so we need to go back to our original source code and change that to a float. Now, if we open the inspector again, we'll see a different error. So on line 118, this SD rombu is not found. So scrolling down to that line, we can see this place here where we're calling this function that doesn't match the name that we used in the function definition above. So again, we go back to our source code, change that, and now we'll get a proper render again. While this does work as it is, there is one more step that we should take to keep things clean. So open the inspector again and scroll down to our operator's code. Note how it renames various things, including the thisMap function and the names of the operator parameters and so on. That helps prevent names from different operators from conflicting with each other and make sure that they're pointing at the right things. But if you look at the SD rhombus function, it didn't get renamed at all. That might be okay if you only have one of these in your scene, but what if you had two of them? So we're going to close the inspector, and then on the code dat, make sure the viewer is off, and then we're going to right click that and choose undock. Then select our custom operator and copy and paste that, and then remove that down here. Now we have two custom operators with independent parameters that are sharing the same source code dat. We undocked the code dat first so that it didn't get duplicated when we pasted the copy. Select both custom operators and use Alt-Shift-R to open the Editor Tools menu. And under Combine SDFs, choose Simple Union, and then connect that to the renderer. And now that will give us an error. Go back to the renderer, open the inspector again, and we'll see that we have an error here saying SD rhombus function already has a body. So scrolling down to our operator code here, we can see that we've got two different operators here. We have two copies of this main function here, but the renderer automatically renamed them to customOp1 and customOp2, and then renamed the things inside it to match. So those are fully separate from each other. But since our SD rhombus function didn't get renamed, we just have two identical copies of it, which means that it's conflicting names, which is going to cause an error. So even though the code is coming from the same original dat, there are still two copies of it that are being modified in different ways, with their names being altered. Since the SD rhombus doesn't get renamed, the duplicate copies of it are causing that error. So to get around that, in our original code, we're going to close the inspector, go back to our code, and then we're going to rename our SD rhombus function and add a capitalized this underscore to the beginning of the name, and then we're also going to update it where it's called down there. Now the error goes away. If you try changing the parameters on one of the two, so maybe decrease the width, increase the height, decrease the thickness, or something like that, you'll see that there are now two copies of the shape and they're being combined together in the final rendering. So if you go back to the inspector and scroll down, you'll see that there are now two different copies of this SD rhombus function, but their names are different since they have these prefixes, so they're no longer conflicting with each other. So in general, any function that you define for your custom operator or any global variables that you define are going to need to have this prefix, and this has to be fully capitalized. And that will tell the renderer to add an automatic prefix to keep things distinct. And that's the end of our scene. Custom operators are a great way to combine your own custom code with all the other features of RayTK. While we use them to create 3D SDFs in this tutorial, they can also be used for all sorts of other things, including transform filters, 2D patterns and fields, and lots more. If you come up with some interesting custom operators, feel free to send them over, and I'll look into including them in the toolkit itself. Thanks for watching. Check out my Patreon for access to scene files, exclusive tutorials, and more. Make sure to like and subscribe, and I'll see you next time.